Welcome back, stats friends. This is going to be your notes for doing a confidence test on the difference of two means. So let's look at this helium problem. So we'll read through it. It says, after buying many helium balloons only to see them deflate within a couple of days, Aaron and Jenna decided to test if helium balloons deflate faster than air-filled balloons. To find out, they bought 60 balloons and randomly divided them into two piles of 30, filling the balloons in the first pile with helium and the balloons in the second with air. They then measured the circumference of each balloon immediately after being filled and again 3 days later. The average decrease in circumference of the helium balloons was 26.5 centimeters with a standard deviation of 1.92, and the average decrease of the air-filled balloons was 2.1 centimeters with a standard deviation of 2.79. So what have we got going on here? Well, this is not a case where we are doing an observational study. We are not sampling, but we're doing an experiment. So if we think about the design of this experiment, we start with 60 balloons, and those 60 balloons are randomly assigned to two groups. We have 30 balloons that get helium, and then we get 30 balloons with air. And what we're comparing in those is that we are comparing the change in the circumference of those balloons. Okay, so keep in mind, we've got an experiment, not a study here. And so in this, we're going to let H equal our helium balloons. This, by the way, is population 1. And we're going to let A equal air-filled balloons. This is our population 2. N sub H was 30, as was N sub A. And we were told that the mean change in circumference for the helium-filled balloons was 26.5 centimeters with a standard deviation of 1.92. And for the air-filled balloons, the mean difference in circumference was 2.1 centimeters with a standard deviation of 2.79. So if we compare those two mean values, there is some evidence that that the decrease for helium was greater than the decrease for air-filled balloons. So our question is, do these data provide convincing evidence, right? That suggests that we're going to do a significance test, that helium-filled balloons deflate faster than air-filled balloons, right? So if helium balloons deflate faster than air-filled, then we would look for the change in circumference for helium to be greater than the change in circumference for the air-filled balloons. So here's our 4-step process. We want to perform a test, right? And these are our hypotheses. H naught would be that the mean for the helium equals the mean for the air, or that mean for helium minus mean for air equals 0. Our alternative hypothesis is going to be that the mean for the helium is actually greater than the mean difference for the air, or mean for helium minus mean for air is greater than 0. And we're going to do this at the 5% level, so alpha equals 0.05, where mu sub H is the true mean difference of helium-filled balloons after 3 days, and mu sub A is the true mean difference of air-filled balloons. So our plan is we're going to conduct a 2-sample, right? 1 sample from each of 2 populations. We're doing means, so we're going to do a t-test for the difference between our 2 means, for mu sub H minus mu sub A, if our conditions are met. So our condition is random. For an experiment, right, it's that the data come from 2 groups that were randomly assigned our treatment. So this is two groups of balloons that were randomly assigned helium or air. Those would be the treatments of our experiment. The 10% condition is not necessary here because we did not do any sampling. And for mean, we do a normal large sample. Again, like the previous problem, we don't know the distribution of the population, so we look at our sample sizes. And in both cases, we had samples of size 30, which is greater than or equal to 30. So our large sample condition is met. To do, we need to find our test statistic and our p-value. So our test statistic is going to be our mu1, which is our mu-h, minus mu2, which is our mu-a. So that's going to be 26.5 minus 2.1, compared to our null, which is going to be 0, because if those means are the same, we subtract and we get 0, divided by our standard deviation of our sampling distribution, which is going to be our standard deviation from the helium sample, which was 1.92 squared, divided by its sample size of 30, plus, right, again, we add these variances, 2.79 squared divided by 30. We calculate that, and we get a t-statistic of 39.46, a test statistic, right, with a p-value coming from a t-distribution, right? So we have a t-distribution with the degrees of freedom of n minus 1, which for us is going to be 29. Both samples were of size 30, so they are the same, right? And when we do this, degrees of freedom of 29 puts us way out towards the end, where the area underneath that curve is approximately 0. By calculator, we would do a 2-sample t-test. And let's do that. So pull out our calculator. We're going to go into stat test. And this time we're looking for a 2-sample t-test, right? And in this we can put in data or we can put in stats. In this case we have statistics. So when we select that, our screen changes and it asks us for our first mean, which was 26.5. Our first standard deviation, which was 1.92, and our sample size, which was 30. Our second mean was 2.1. That standard deviation was 2.79, and that sample size also 30. For our alternative hypothesis, we are looking for where mu1 minus mu2 was greater than 0, or where mu1 was greater than mu2. Okay, we never pool, so that's an easy answer, and then we calculate. So let's go back and put what we entered in here. So in here we had x1 was 26.5, s1 was 1.92, n1 was 30, x2 was 2.1, s2 was 2.79, n2 30, and our alternative hypothesis was that mu1 was greater than mu2, right? Where that was helium, 2 was air. The result of that 2-sample t-test is that we get a test statistic of 39.460 with a p-value of 1.98 times 10 to the negative 40, right, which is just too many zeros to even write. So that is approximately 0 with a degrees of freedom of 51.435. So our conclusion is, because the p-value of approximately 0 is certainly less than an alpha of 0.05 or any reasonable alpha level we might pick, we reject H0. Right? There is not convincing evidence that the helium balloons deflate faster than air-filled balloons. Right? So to interpret this p-value that we got in part A, we would make a statement something like that, and that would be that if the difference between the two true mean decreases in circumference or 0, right? So if the true mean difference was 0, which was our null hypothesis, then the probability of getting a difference as large as we did, so that would be of 24.4 or more, right, more extreme than that, is approximately 0. I've got to go back here. When we reject H0, there definitely is convincing evidence of that alternative hypothesis. Okay, so there we go. You got that, and you can take it from here.